We have a rather funny looking equation here for the Hermite polynomial of order n. So what I suggest you do is you pause the video and try and get a feel for this formula by plugging in, for example, 0, 1, and 2, and then also trying to show that this thing holds for a general value of n. So pause the video and do just that. Let's start with a rather trivial case where n is equal to 0. Now, if n is equal to 0, then we have this thing here, which should be considered as a linear operator, raised to the power of 0. So whatever you raise to the power of 0, that's just going to be 1. So the end result of this thing is 1. And we do know that 1 is indeed the Hermite polynomial of order 0. So that was perhaps a bit too trivial to see what was going on here. So let's now look at the case where n is equal to 1. So then we have 2x minus d dx operating upon 1. So what do we mean by this? So again, this is a linear operator. So first we have this term 2x operating on the function 1, and then we have minus d dx operating upon the function 1. How should you interpret this? 2x operating upon the constant function, that's just 2x multiplied by that function. And then finally, we have d dx operating upon that function, that constant function 1. That's just taking the derivative of that constant function. So not a whole lot will be left after taking the derivative of a constant function. So the end result is 2x. And we do know that 2x indeed is the Hermite polynomial of order 1. Okay, so far so good. Just to make sure that you really understand what's going on with these operators here raised to a certain power, pause the video and try to show that this thing also holds for n equal to 2. So what's going to be happening for n equal to 2? For n equal to 2, we know that the Hermite polynomial of order 2 needs to be 4x squared minus 2. So that's the result that we're working towards. Question is this equal to this thing here where we have the operator raised to the power of 2? Now something raised to the power of 2 means something multiplied by itself basically. So you can write this as 2x minus d dx applied twice. So this is how you should interpret these powers, applying it twice. So we apply it twice, that means we also write it twice. And then this new operator is operating upon the constant function 1. Now we do know what this part is over here. We've just calculated that for the Hermite polynomial of order 1. So the end result is 2x, as we've seen. So now what we need to do is we need to have the operator that we have here operating upon the function 2x. So first we have 2x times 2x. That's going to give us 4x squared. And then the next step is going to be the derivative with respect to x of 2x. So that will be giving us minus 2. And indeed, good news is that this is indeed the Hermite polynomial of order 2. Now, you might have been tempted to do the following when you were seeing something like a square of this operator here, 2x minus d dx squared. You might be tempted to say that these are just numbers basically, and you might want to write something like 4x squared minus 4x d dx minus d dx squared or something like that. But that's obviously wrong. Well, perhaps it's not immediately obvious that this is wrong, so you might want to think about why exactly this is wrong. We're not going to discuss this here. This will come back in a later chapter, but don't yield to the temptation of just considering this as numbers that would obey all sorts of properties that you're used to numbers obeying. So these are not numbers, these are operators. So don't make that mistake here. Okay, by now we have a pretty good feeling for how these operators work, and what we can do now is try and show that this is true for the general case for n equal to n. Now the way to do that would just be mathematical induction. So pause the video, start from the assumption that the formula holds for n, and then also show that the formula holds for n plus 1. And then based on what we have here, we have shown that this is true for all possible values of n. So what is our task here? Our task is to show that the Hermite polynomial of order n plus 1 can be written as our operator 2x minus d dx to the power of n plus 1 operating upon the constant function 1, assuming that a similar formula holds for n rather than for n plus 1. Now, since we know that the formula holds for n, it's a good idea to try and write this formula in such a way that the formula for n also makes an appearance there. And that we can do by writing this power n plus 1 here as the following set of operators. So we have first the operator 2x minus d dx, and then operating upon the operator 2x minus d dx taken n times. So this is simple rewriting of our power n plus 1 here. And then the good news is what we have over here, so the stuff between square brackets here, if we assume that the formula is valid for n, then this is just basically hn of x, right? So we can write this as 2x hn of x minus, and then the derivative hn prime of x. Now we do know, thanks to our recurrence relationships that we have derived earlier, that the derivative of the Hermite polynomial of order n over here is 2n the Hermite polynomial of order n minus 1 x. And we also know, if we write this like this, that's another recurrence relationship that will allow us to draw the conclusion that this is exactly equal to the Hermite polynomial of order n plus 1. So we just make use of two recurrence relations, one after the other, and then we have shown that the formula is indeed valid also for n plus 1.